Hello, Science Lines. I am Lara. This is Theatre of Science. Sorry, my child got into my room over the Easter holidays and drew these pants on the board. I just quite like it. It's quite good. So I hope they're not too distracting and they just add a bit of interest to this IGCSE physics lesson, which will already be quite interesting. We're learning about evaporation. You don't have to have seen any of the previous IGCSE lessons to do this. It's a lovely standalone lesson. And you don't need very much stuff, but hopefully it's going to make us really question things in our everyday life that we've never questioned before. I'd like you to please, I'm using like really freshly boiled water because that's what I've got here. You really don't have to do that. If you don't have an adult with you and you don't usually use boiling water, definitely just use warm water, will be completely fine. You can use very hot water if you're allowed to, but you need 2 mugs or cups of very hot water. They've got to be the same temperature, okay? Yeah, that's all. While you're getting that sorted, I will very quickly recap the last lesson, because if you're watching live, then it was 2 weeks ago before the Easter holidays. So I showed you this, and we were talking about what happens and what it's called when solids turn into liquids and then when liquids turn into gases, etc. So we looked at how when a liquid turns into a solid, that is called freezing. That's probably not big news to any of you. When a solid ice cube, for example, turns into water, then liquid water, we call that melting, don't we? A gas like water vapor in your bathroom, maybe if someone's had a shower, sticking to a cool mirror and turning back into liquid water, that's called condensing. And then we looked at how liquid into gas is called boiling. And I said, don't get that confused with evaporation. We'll do evaporation next lesson. And next lesson is here. Hooray! So what I'd like you to do, are you ready for this activity? Are you ready? I'm not sure you're ready. What I'd like you to do, please, and you can keep yours on the table, I'm just doing it up here because it's better telly. Can you get one of your cups full of warm or hot water and pour it into a bowl? That was today's activity. I hope you enjoyed it. So now we've got probably roughly, hopefully, the same amount of water, one of which is in a cup and one of which is in a bowl, yeah? So you've got 1 cup of water and 1 bowl of water. What I want you to think about, and a lot of you will just know this, is what's going to happen. What are you expecting? If we come back to this water in maybe 5 minutes' time after I've yacked on a bit, what will we find? Shall I show you? Shall I make it more visible? Yeah. So bowl of water, cup of water, both the same temperature, different vessels. What are we going to observe when we come back? You can actually observe something right now, can't you? You can see stuff coming up. Anyway, don't worry too much about it, and I'll recap a little bit about solids, liquids, and gases, and then we'll come back to that and we'll see what's happening. So a very quick recap on boiling. Then we've talked about this quite a bit. Particles in solids, like, I don't know, tables or ice cubes, or what else is solid? Like forks. The particles are very rigidly bonded together. So we've talked a lot about how all particles in the whole universe really are all vibrating a little bit, but particles in solids are really packed together and they're just sort of vibrating on the spot. Yeah, they're certainly not free to move. Particles in a liquid are kind of free to move. They're bonded, but they are moving around each other all the time. I think it's helpful to picture a ball pool. The bonds between particles of liquid, and when I say particle at the moment, I'm just talking about these little balls. They're constantly forming and breaking, but they are bonded together, but they can move around each other. And in a gas, the particles don't care about each other at all. There's no bonds between the particles. They are free to move. And we say that if the particles in a liquid get enough energy to break apart and be free like this, then that is what boiling is. It's a liquid usually getting so hot that the bonds between the particles break completely and the particles are free. Right. Everything all right with that? Okay, cool. So some questions to intrigue and annoy you. We did do this 2 years ago when I first taught this module. I wonder if some of you were certainly watching. I don't know if you'll be able to remember. Answer these with your best guess, please. When you boil water, it bubbles. What are the bubbles made of? That's your first question. When you boil water, it bubbles. I brought my awesome seafood kettle so that we can actually see water boiling in real life. Can you imagine? People say physics is boring. But later on. And the second question is, a water molecule is 2 atoms of hydrogen bonded to 1 atom of oxygen. That's quite a lot if you haven't yet learned about atoms and molecules, but you'll just sort of have to take my word for it. We'll think of a hydrogen atom as being a ball of hydrogen and an oxygen atom as being a ball of oxygen. And when more than one atom gets bonded together, you call it a molecule. So water is H2O, H2, 2 hydrogens, and 1 oxygen all bonded together, okay? So this is 1 water molecule. If it gets broken apart, it's not water anymore, it's just hydrogen and oxygen, like floating free. A water molecule is 2 atoms of hydrogen bonded to 1 atom of oxygen. What happens to the bonds between the atoms when water boils? I'm really glad I put these questions in because the first one's sort of just for funsies, actually. The first one's just a cool fact that I didn't know until I started planning this lesson. The second one is it's very important that you know this, like for your GCSE, if you're going to do one. And a lot of people I was finding on Facebook 2 years ago and this year didn't know this. When you boil water, it bubbles. What are the bubbles made of? Lara, please can we see your kettle boiling to help our understanding? Oh, all right then. I know it's not very good for the environment, is it, boiling water? It takes a lot of energy. But I figure that because I'm the teacher and I'm recording this for lots of people, then it's all right if I do it. And I promise you I will drink this warm water afterwards. I like warm water as a drink. All right, what are we observing then? I've put my kettle on to boil. Immediately bubbles start to form. Very small bubbles at first, and then the full, what my family calls blobby blobby time, kicks in. But what are those bubbles? It's beautiful, isn't it? Have you got some answers for me? I tell you what, I'll do a quick sketch on the board, and when I finish my around the pants, and when I finish my quick sketch, then I'll give you the answers. There we go. I'm hoping that the noise of my neighbour cutting their hedge isn't quite as loud for you as it is for me. I don't know what my neighbours got against hedges, honestly. All my neighbours are always attacking hedges with loud machinery. Anyway, right, are you okay? Have you thought about that? Shall I tell you now or shall I keep you hanging? Should we go to the... Should we... No, I'll tell you now. And then we'll get to our water and observe what's happened. When you boil water, it bubbles. So if you've ever left a cup of water on the side for a little bit and found that bubbles have formed all the way around the edges of the cup, or if you've started heating like spaghetti in a pan of water, the little bubbles forming around the edges, they are air. That is air particles that were dissolved in the water coming out and forming bubbles. But the proper full-on blobby blobby time water that happens when water boils, that is actually water. It's water particles that instead of being the ball pool where they're all the bonds between them are breaking and forming and breaking and forming, it's water that has got so much energy that the particles have broken free of their bonds, and you've got like pockets of water vapor, so sort of little bubbles of gas inside the liquid water. I know, right? It's good, isn't it? I've done that thing where I tell you the answer and I've already written it on the PowerPoint, so I could have just showed you. Water! The bubbles are where the water particles have gained enough energy to break their bonds, spread out, and become a gas. That's a good way of wording it, wasn't it? Well done, past me. This is the more important question, really, that a lot of people got wrong. A water molecule is 2 atoms of hydrogen bonded to 1 atom of oxygen. What happens to the bonds between the atoms when water boils? Nothing! Nothing happens! The bonds between the water molecules break, but it's still water. Like, it's still water vapour that you're seeing in the air. It's not oxygen gas. And like when you boil a kettle, oxygen and hydrogen gas doesn't come out of your kettle, okay? It's so important that you know and fruit. I really do need to wipe off my whiteboard, but I want to take a picture of it first. I've drawn some water particles. So water is H2O, right? That is one water particle. That's another water particle. That's another water particle. Water particles are bonded together like this in liquid water, and indeed in solid water. Not necessarily like this, so there's no chemist watching. But yeah, water particles are bonded together. When liquid water gets hot enough, it's not always heat, sometimes it's to do with pressure, but we're just going to talk about heat. If you heat up these water particles enough, they gain enough energy, they move around so much that these bonds break and the water particles are free. So it's a gas. But the water particles are still water particles. Do you see what I mean? At no point do we have oxygen gas and hydrogen gas floating around. So that is important to remember, and I will be testing you on it later at the end. Right. So let's talk about evaporation, because that's what this lesson is supposed to be about. Let's talk about the difference between boiling and evaporation. Can we now, I think we've left it long enough, go back to our cup of hot water and I think I've still got some cocoa powder on my head from the moon lesson that I just taught. Let's go back to the bowl and the mug. If it is safe to do so, children, you can carefully test the temperatures of the water if you like, but do be careful because the water might still be really hot. I'm holding the sides of this bowl and I'm feeling pretty comfortable. So that was freshly boiled when I poured it in, and now that's lovely. That's like a medium bath temperature. This one, well, be careful putting your fingers still in the mug. That's hot. So that probably wasn't big news to you. My question that I want you to think about is, why has the water in the bowl cooled down? Why has the water in the bowl cooled down? Why is the water in the mug still hot, but the water in the bowl has cooled down? Now, a lot of people on Facebook yesterday were just writing, because the bowl's got a bigger surface area. And that is true. And that is something to do with it. So if you don't know what surface area is, it's basically just how many of the water particles are on the surface. So this mug, it's got the same amount of water in it as the bowl, but the water particles in the bowl are more spread out, right? It's got a bigger surface. So that's an answer, yeah. But why does having a bigger surface area mean that the bowl has cooled down faster? And that's where everyone got totally stuck and started saying weird things. So, why is the water in the bowl cooled down faster? Because the bowl's got a bigger surface area. Why has having a bigger surface area meant that the water in the bowl has cooled down faster? Now, on Facebook yesterday, people were saying things like, because there's more cold air particles in contact with the water. So what are they thinking about there? There's more, the air above the water is colder, is it, than the water in the bowl? So why would that make a difference? If you watched our energy lessons, you might remember that energy gets transferred from things that are hot to things that are colder. So we're not thinking like, oh, well, the air above the bowl is colder, so the cool air particles are knocking into the water and like passing on the coldness. That's not a thing that happens. The bowl is losing heat. It's not gaining coldness. Is that all right? What is heat? It's just particles vibrating a lot. The water particles are vibrating a lot because they're hot. And they are passing their vibrations onto the air, yeah. But you might remember, if you've been following this whole course, we have learned about how heat gets passed on, and we've talked about conduction. So your body is warm, you touch a metal thing, which is colder. Your body's particles are vibrating a lot. They vibrate into the particles of metal, make the metal vibrate more, and heat gets passed in that way from your body to the cold metal, yeah? And that is called conduction. And in our lesson about conduction, it's kind of like a sort of domino effect, right? Heat goes from the thing that's vibrating a lot, your hand, into the thing that's not vibrating much. We talked about how conduction happens very well in solids, but it doesn't happen very well in gases. We actually talked about how if you want, say, heat to not pass from your nice warm house into the outside, double glazing is a good idea. Put like a gas or a vacuum inside 2 layers of glass and that'll stop heat passing. So what's going on? It's good, isn't it? This is how I learned physics. I learned physics really late from a teacher who would just ask me a question and I'd be like, yeah, that's obvious. And then they'd be like, yeah, but why though? And I'd be like, I don't know. I don't understand anything anymore. I don't know how doors work. What have you done? Okay, let's talk about evaporation, and that will then you will know. You will know the answer. So we've talked a lot about how particles in a liquid are always moving around. All particles are always moving around all the time. Are you okay with the fact that when you heat particles up, they move more? Yeah, here's an amazing PowerPoint effect telling you that. Well, not all of the particles are moving at exactly the same speed. This is the key thing to know about evaporation. When I say water particles are a certain temperature, not all of the water particles are moving at exactly the same speed. Some have more energy than others. And that makes sense, doesn't it? Like when you think about it, that makes sense. Obviously, when I flick a kettle on, not all of the water particles in the water all move at the same amount at the same time. They don't all gain the same amount of energy all at the same time. Obviously, really, there are going to be some that are moving slightly more slowly and some that are moving faster. When we talk about the temperature of water, what we mean is like the average amount of energy that all of the particles have. Your time is over. So yeah, the temperature of a liquid is a measure of the average energy of all of the particles. So if this one's moving really, really fast and this one's moving really, really slow and this one's moving in the middle, then we've got a middling temperature of the water, okay? Evaporation is when the particles on the surface of a liquid, the particles on the surface of a liquid with the most energy escape. I was worried you wouldn't understand that. So again, I did this PowerPoint special effect. Here's a water particle at the surface of some water going pew pew and escaping, becoming a gas, right? Breaking free of its little brothers and sisters. There we go. It's become gas. Notice that the particles underneath aren't doing this, because they can't, can they? Because they're buried underneath. It's only the particles on the surface that can evaporate, like go into the air. And it's the water particles on the surface, I keep saying water, any liquid, but it's the particles on the surface that have got the most energy that escape. Right, what does that do to the average energy of the particles? Like the temperature of the liquid. Are you all okay? I feel like I've done that quite fast. Are you okay with the fact that when I talk about like the temperature of the liquid, I just mean the average amount of energy that all the particles have got? If all of these water particles have got loads of energy, then it's a high temperature liquid. If they've hardly got any energy, that's a low temperature. We'll do more about temperature in another lesson. I've got a thing here on my PowerPoint which I'm hoping will help you to understand and won't make things more confusing, but you be the judge of that. Right. We'll start really simple. We won't even start. We'll just go simple. To help us visualise things, imagine 6 water particles, okay? And these numbers are how much energy they've got. This one's got 4 amount of energy, this one's got 3, this one's got 2, and that one's got 1, that one's got 1, and that one's got 1, okay? Remember, please, temperature is the average energy of the particles. So do you know about averages? Can you work out the average amount of energy these particles have? So imagine you've just got to add up all the numbers, right? And then divide by how many there are. And that gives you the average amount of energy that a water particle has in this weird cup of water that only contains 6 water particles. What's the average amount of energy that each of those particles has? I'm not going to spend ages on this, because if you can do it, you've probably done it. And if you can't do it, you'd probably like me to just tell you. So you add up all the numbers, 1 plus 1 plus 1 plus 2 plus 3 plus 4, and that equals 12. And then you divide that by how many particles there are, and that gives us 2. So the average amount of energy that one of these particles have got is a 2. Okay, now let's say that the particles on the surface with the most energy, they leave. There's the 4 gone, there's the 3 gone, there's the 2 gone. We've only got half as much water as we had before. What's the average amount of energy the remaining particles have? Oh, Lara, it's 1 plus 1 plus 1, which is 3, divided by 3, which is 1. Can you see? Does that help you to know why the water in the bowl cooled down? So the water particles in the bowl. Some of them had loads of energy, some of them had not very much energy. The ones on the surface of the water that had most energy, they escaped into the atmosphere, which meant that the average amount of energy that the particles had that were left was lower. Is that okay? Just picture this as being a big ball pool where all the balls have got like 1, 2, 3, 4 on them. If I take out loads of 4s, then the average amount of energy that the particles that have got left is less. Is that okay? I feel like I'm doing the thing that my old physics teacher used to do, where it's just like words, words, words. Do you see? Do you understand? Yes? You see? And I'd be like, no, but if I say no, you'll probably try and explain it again. So yeah, let's just move on. Right. Back in my power. Evaporation lowers the average amount of energy the particles have. In other words, it lowers the temperature. It makes the liquid cooler, is what evaporation does. Okay, the water in our remaining cup, remember that? I've actually drunk most of it. I'll have to top it up again. It is evaporating, but very slowly. So this is one of the big differences between evaporating and boiling. Boiling happens when you get stuff really hot. Again, it could also happen if you sort of reduce the air pressure around it, but we'll concentrate on temperature. Evaporation happens all the time. You might have found that if you've left a glass of water on the side in your room for ages and ages and ages and ages, you come back to it and there isn't any water there, because the water has evaporated. But there are 3 things you can do to make water evaporate faster, liquids evaporate faster. If you've still got the water in your cup, which I'm hoping you have, how could you speed up how quickly the water in your cup is evaporating? I've said, I'm not even going to show you, I've put on the screen here, there are 2 ways and both involve your body. And then I've written underneath that, be careful and sensible, please, I can't afford to get sued because you stuck your knee or something in some hot water. But there are, in fact, 2 ways that you could use your body to make the water in this cup evaporate faster. There's 3 ways you can make liquids evaporate faster, but we've already done one of them. But there's another 2 ways you can make liquids evaporate faster. And you can do them both with your body. Please be careful. If your water is very hot, please be very careful. The first one most people on Facebook just got straight away yesterday. The second one, a couple of people got. Okay. A lot of you will be saying blow on it. Yeah, you're right, actually. Why? Why? You've got to be so careful here because it's so easy to get how fast something evaporates confused with like how much it cools down. So you're blowing on it. Why does blowing on it make the particles evaporate faster? Why would blowing across the surface of a liquid make particles on the surface escape faster? Come on, let's go. PowerPoint answer. How fast a liquid evaporates depends on the surface area of the liquid, which we've already done. We made the surface area bigger and it got cooler faster, and that's because it evaporated faster as well. The air movement over the surface, so yeah, blowing on it, definitely. And temperature, so warmer water, for example, evaporates faster, which is, it's a bit weird, isn't it? Because surface area does make stuff cool down faster, but it also increases the rate of evaporation. And warming stuff up makes the particles evaporate faster. I think, well, very quickly I'll talk you through it and then I'll give you this little question sheet to do. When you blow over the surface of the water, it makes the particles evaporate faster, kind of in the same way as like if you've been to a big sports event and they open the doors, if everyone started to leave, but then people just stood chatting right in the entranceway, it'd be very hard for everyone else to get out, wouldn't it? Whereas if you open the doors and everyone like ran for the hills, that would get everyone out a lot faster. It's the same sort of thing. If you blow across the surface of a liquid, you are removing those water particles, or whatever the liquid is, that have just evaporated. So more particles can follow, basically. And the temperature one, well, you're giving the particles of the liquid more energy. So if they've got more energy, it means more of them can break free of their bonds and be in the air. Is that okay? I feel like you've done enough on that. Have a look at this sheet. Here we go. Which of these would make the water evaporate faster than just the glass of water being left alone? And I've said, can you explain why or why not in a couple of words? So you've got 6 different scenarios here. Imagine I get a glass of water and I move it from the shade into the sun. Is that going to make the water evaporate faster? And if it is, why? Or if not, why not? Repeatedly pouring water from one glass to the other. Is that going to make the water in the glass evaporate faster? Yes or no? And why? Just a couple of words. You don't need to go into loads of description about what's happening between the bonds. You could just say like, yeah, because hotter or whatever. Putting the same amount of water into a taller glass. Is that going to make it evaporate faster or not? Why? Blowing hot air over the surface of the water. Gently heating the bottom of the glass of water. And blowing cold air over the surface of the water. Have a go at those. I'm looking at my bowl and my cup and thinking the water in the bowl also cooled down faster because heat was conducting through the sides of the bowl. So if you have seen our conduction lesson and you said something like that, then yes, well done. How are you getting on? Should we do answers? I think there's one that I've got slightly wrong, actually, or one that I could have done a bit more detail on, or I said that it was one reason and it probably the other reason. Well, there's 2 reasons. Yeah, some of them have got 2 reasons. Can you remember what makes water evaporate faster? Surface area being increased, temperature being increased, or having air blown over the surface. And some of these, 2 of those things are happening. Okay, should we go through it? Moving water from the shade into the sun. Well, hopefully most of you said, yeah, that would make the water evaporate faster because it would make the water hotter. So if you're increasing the temperature of the water, then you're giving those particles more energy. So they break their bonds and go into the air faster. Repeatedly pouring water from one glass to the other. Yeah, I said that would make it evaporate faster because of the bigger surface area. But Alice, watching on Facebook yesterday, pointed out that it would mean that there was air being blown over the surface as well, wouldn't there? Because you're pouring the water, so it's like the water's moving past the air instead of the air moving past the water, but it would still have the same effect. So I really should have put also like air moving over the surface of the water. Putting the same amount of water into a tall glass. No, I think if anything that would make it evaporate more slowly, because it would be harder for the water particles to leave the surface, right? You've sort of created a bit of a blockage. They're protected, aren't they, from any wind that might be passing by. Less air movement over the surface is what I would say if I was doing an IGCSE physics exam. Blowing hot air over the surface of the water. Yeah, this was 2, wasn't it? So you're increasing the temperature of the particles on the surface, and you've got air moving over the surface. So that would definitely make it evaporate faster. Gently heating the bottom of the glass of water. I thought that might trick you because you're heating the bottom of the glass of water and its evaporation happens on the surface, but you're still increasing the overall temperature of the water particles. You're giving the water particles more energy. So that would make it evaporate faster, certainly. And blowing cold air over the surface of the water would also make it evaporate faster because, again, there's more air movement over the surface. It's just you're not increasing the temperature of the water. Phew! Is that all right? Okay, so the very last thing I want to do is just to doubly, triply check that you've grasped the difference between boiling and evaporating. So I'm killing time because I'm wanting you to get those answers down. But so I've got, I think it's 7 statements for you, and it's either a statement or evaporation, or it's a statement about boiling, or it's a statement about both, or maybe neither. So what I want you to do is read each of these statements and say, does it describe boiling or evaporating or both or neither? And I was quite pleased at how this, I'm glad I stuck this in. This is the last thing I wanted to do because it was catching quite a few people out, especially if you're not clear on the difference between atoms and molecules. Here we go. Only happens at the surface of a liquid. Is that sentence talking about boiling, evaporating, both, or neither? Happens when liquid in normal conditions on Earth's surface is at any temperature. Long sentence, sorry. Is that describing boiling or evaporating, neither, or both? Bonds between atoms are broken. I've put a little molecule here of water for you, oxygen with 2 hydrogens bonded to it. That's 1 particle of water. So that's an oxygen atom and 2 hydrogen atoms. Bonds between the atoms are broken. Is that boiling or evaporating or both or neither? A liquid turns into a gas. Is that boiling, evaporating, both or neither? A liquid cools as it happens. Bonds between molecules are broken. Bubbles of gas form when it happens. And a reminder that hopefully there is a post on my Facebook page right now if you're watching live, where if you want to, if you look up Theatre of Science on Facebook, because you've got a Facebook account, you can go over and comment. And I'll say hello. If you haven't got a Facebook account, well done you, frankly. Don't feed the nasty corporate machine. Well, obviously you have to feed the YouTube one because you're here, but that's fine. I can see that you're watching and I very much appreciate it. Are you ready to go through it? Let's go through it. Only happens at the surface of a liquid. That is definitely evaporating only, isn't it? Boiling can happen all over the place. We saw my kettle start to boil water from the bottom. Happens when liquid in normal conditions on Earth's surface is at any temperature. That is evaporating only. Sorry, that was a little bit clunky. It's because you might have heard of this thing of like you can't make a proper cup of tea on Mount Everest. So technically, well, not technically, just in reality, liquid can boil if there's just not any air particles pushing down on it, right? If you take a cup of water into space, there's no air particles to push on that water and keep it in place, so the water will just start to float freely, like as a gas. But if you've got like just a cup of water on Earth's surface where gravity is normal and air pressure is normal, you would never find, would you, that water was just suddenly boiling. Whereas you find that you come back to it and there's no water left because it evaporated. Okay, so evaporation happens at any temperature on Earth's surface in normal conditions. Bonds between the atoms are broken. No, that is neither. That doesn't happen with evaporating or boiling. The hydrogen and oxygen stays bonded together. It's always water, even if it's water vapor. Hydrogen isn't getting ripped off oxygen. You don't get more oxygen to breathe or something. Liquid turns into a gas. That is both. Boiling is a liquid turning into a gas, and evaporating is particles of liquid gaining enough energy to be free and not bonded to each other in the air. So that is also a gas. A liquid cools as it happens. That is just evaporating, for sure. Bonds between molecules are broken. That is both, yeah. So if you're boiling something, then you are breaking the bonds between the molecules so that it can become a gas. But the bonds are breaking because that's how water gets evaporated into the air, right? Bubbles of gas form when it happens. That is boiling only. There's no evaporating. It doesn't involve bubbles. All right, so hopefully that's helped. You might know about evaporation causing things to cool down because of like sweat. I don't know, I feel like it's a sort of fairly well-known fact that you cool down, sweat cools you down because what is happening is water particles are released onto your skin. Can I flip that around now? Water particles are released onto your skin and heat from your body gets passed to those water particles and then they escape. So that's how heat from your body sort of escapes. It's using the water particles to do that. All right, you lot, that is the end of my lesson on evaporation. I hope that you enjoyed it. I really did. We've got 2 more solid liquids and gases lessons left. And then I want to do 3 lessons to take us to the end of term about how electricity is generated, like wind turbines and solar panels and all that stuff. And then we've got a half-term holiday. And then we've got our last module, which is radioactivity. And then that's it. I will have taught an entire IGCSE physics module live into the internet for the second time. So yeah, do join me next week for more IGCSE physics. I'm going over to my Facebook page now to see if you have managed to leave me some comments on Facebook. If you happen to be new, if I kept any new people, given all the technical problems that I had today. Oh yeah, Lewis. Hello, Lewis. How this business model works is, it is ridiculous. Everything that I do is free. Everything. I don't do any secret one-to-one tuition or Zoom lessons. I am trained to teach physics in the classroom. I have classroom experience. I have a first-class science degree and a first-class drama degree, and now this is my whole job. It's just all come together. And it only works because people who watch pay me a small amount per month. Most people have signed up to support me with £5 a month, and that is entirely what pays for like all my planning and my teaching. It's so good, isn't it? It's so good. You would never have thought that could possibly be a thing, but it is. You lot are amazing. So if you go to my about section on YouTube, which you are on, or you go to the top of my Facebook page and click sign up, but you should go to my about section on YouTube. It takes you to this website called Coffee. Basically, hopefully anywhere where it says sign up takes you to this website called Coffee. You send me £5 a month, and if all these lessons weren't enough, I also send you nice things through the post. Really, loads of nice things. Like I can't even hold them all in my hands. So yeah, sign up. Send me £5 per month. I will send you nice things. Equals job for me and free lessons for you. It's all working out really well, isn't it? Okay, Lewis is here. Hello. Bastian is here still. Excellent. Hello. Freya and Hannah are here. Kai's here. Rocklin's here. Molly's like, yep, it's all working. Why ain't faffing around? Oh! Rocklin says, so this is why a hot drink in a cappuccino mug goes colder faster than the same drink in a tall, narrow latte mug. Yeah. True. Yeah. I think that's probably why cafes put them in those mugs, isn't it? So it will cool down faster, so you've got to drink it faster and then get out so someone else can have your seat. I don't know that. Rocklin found me again. Breathe on it and hold it. Nice, Molly. Boom. Just 2 correct answers in 5 words. Excellent. I thought it would be no for the one heated because it would boil eventually. I thought it would be no for the one heated. Oh, I've closed my PowerPoint, so I can't see what you mean. For the one heated. Oh, I see what you mean. The one that was heated from the bottom. You thought that would be no because it would boil. Oh, yeah, I see what you mean. Yeah, well, I mean, it might boil, but it would also still increase the rate of evaporation. I hope that has answered your question. All right, I'll do a quick refresh, although that's probably everyone, but sometimes it's not. And then I will go. And I will see you all next week. Or if you like YouTube stuff that I do, I might see you tomorrow at 9 a.m. for my astronomy lesson, first astronomy lesson about waves. Or at 10:30 for the Lego Story Show, which is about the moon. Okay, I think that is everybody. I'm going to quickly click newest comment. Excellent. Yes, that is everyone. All right, thank you, you lot. Thank you for your patience with the tech problems at the start lesson. Great. Thanks for your support. Thanks for putting up with the picture of the pants that's on the board. I better fix that for next lesson. I'll see you all very soon. Bye.